In this video, I'm going to talk about a slightly advanced flow control algorithm called sliding window, used in most high-performance protocols today. So recall, a simple flow control algorithm called stop and wait has at most one packet in flight at any time. So this is the basic simple protocol you might say algorithm you might try to implement the first time you're doing reliable communication. So sender sends a packet or a chunk of data, the receiver sends an acknowledgement. The sender, if it doesn't receive the acknowledgement, times out, tries resending. If it gets the acknowledgement, it sends more data. And there's some issues with duplicates. You can maintain a counter, a 1-bit counter, to figure out if there's a duplicate ACK or an ACK to a duplicate or new data. As long as things aren't duplicated for more than a round trip time, stop and wait works. It's great. It's simple. So while stop and wait works correctly, it has one major problem. Let's say you're trying to communicate between Boston and San Francisco. And the bottleneck is, say, 10 megabits per second. So there's a 10 megabit per second link here, or let's say the Boston node can receive at 10 megabits per second. Basically, that's the rate at which you can process data. Your round trip time is 50 milliseconds. And let's just say, for simplicity's sake, we're sending Ethernet frames. So that's the size of the data, so which are basically 1.5 kilobytes or 12 kilobits. Now, our round trip time is 50 milliseconds. That means that San Francisco can send one packet, and if that packet's received successfully, 50 milliseconds later, it'll get an acknowledgement. So we have 1,000 milliseconds per second divided by 50 milliseconds. This means that we can send at most 20 packets per second on this path. Now, 20 packets per second times 12 kilobits per packet is equal to 240 kilobits per second. So this path between San Francisco and Boston using a stop and wait protocol can send at most 240 kilobits per second, assuming no packets are lost, just constant RTT of 50 milliseconds. But the bottleneck is 10 megabits per second. So this means that this stop and wait protocol is using 2% of the capacity of what the communication could be. So stop and wait, while it works, can be astoundingly inefficient. San Francisco could be sending data much faster than what stop and wait allows. So the basic solution that most protocols use today for this problem is something called a sliding window. And sliding windows are a generalization of stop and waits, where stop and wait allows one packet in flight at any time. A sliding window protocol allows up to n packets in flight. So when n is equal to 1, a sliding window protocol behaves like stop and wait. And so let's say we have a sliding window protocol with an n equal to, say, 5 packets. This means that San Francisco can have 5 packets in flight, and simultaneously there can be 5 acknowledgements. There can be 5 acknowledgements coming back from Boston. And the idea here is that if you can set n to be the correct value, then you can keep the pipe full. That is, San Francisco could send data to Boston at 10 megabits per second. So let's say that's Boston's rate. And so Boston can, by configuring the sliding window size, can have San Francisco send data at a rate equal to 10 megabits per second. And so in this particular case, right, if we have an RTT of 50 milliseconds and a bottleneck of 10 megabits per second, let's say that we're sending Ethernet frames, right, 10 kilobits per packet, and we have 20 round trip times. That essentially means that the sliding window is going to be 10 megabits per second divided by 20 round trip times, which is basically equal to 500 kilobits per round trip time. So we're looking at a sliding window of around 41 packets, right? 40 is 480 kilobits per round trip time, so 41 would be 492. And so if we had a sliding window of 40 packets, then we'd actually be able to sustain a 10 megabit connection from San Francisco to Boston with a round trip time of 50 milliseconds. So just to draw a picture, kind of show what this looks like. So here is the original, here's the stop and wait. We have this 1-bit counter, data 0, ACK 0, data 1, ACK 1, data 0, ACK 0. So the sliding window, let's say we have a sliding window of size 3. Well, the sender will send 3 packets. Let's call them D0, D1, D2, and the receiver can then acknowledge them. Right. ACK 0, ACK 1, ACK 2. Well, as soon as acknowledgement 0 arrives, the sender can send data 3. As soon as acknowledgement 1 arrives, the sender can send data 4. As soon as acknowledgement 2 arrives, the sender can send data 5. So this is the basic idea. Rather than having this one packet, you could have many packets. So in the case of having a sending window of size 40, you can imagine there are tons and tons and tons of packets in flight. So let's look at more concretely what this algorithm looks like for both the sender and the receiver, just as we did for stop and wait. So a sliding window sender, first in a sliding window protocol, every segment has a sequence number. So in protocols like TCP, this is usually done in terms of bytes because they can be variable size. For simplicity's sake, we'll just do it in terms of packet numbers. So there's a sequence number for every segment. So the sender maintains 3 variables: the size of its sending window, the last acknowledgement it received from the receiver, and the last segment it sent. And the sender's job is to maintain this invariant, that the last segment sent minus the last acknowledgement received has to be less than or equal to the send window size. So this means that if it has received packet n, right, a packet with a sequence number of n, the sender cannot send a packet past n plus SWS. So let's say we have a sending window is equal to 5, and the last acknowledgement that's been received is equal to 11. Then this means that the sender cannot send a packet past 12, 13, 14, 15, 16. It's not allowed to send 17 until it gets the acknowledgement for 12. When you get a new acknowledgement, you advance LAR as necessary, and you buffer up to sending window size segments in case suddenly you get an acknowledgement and then you want to send a whole bunch of new data. Let's pretend for a second we have a sending window size equal to 3. And so here's packets 0, 1, 2, 3. Let's say 0 had been sent and acknowledged. So our sending window size is 3. The last acknowledgement for the receiver is 0. So LER is equal to 0. SWS is equal to 3. This just means that the last segment sent is equal to 3. So now when an acknowledgement arrives, say for 1, then the sending window can advance. And so now the protocol can send 4. And let's say an acknowledgement for 4 arrives, then the window can advance and it can send 5, 6, and 7. Now, one thing that's important here is that let's say we have a send window which includes 5, 6, and 7, and 5 is lost, but 6 and 7 arrive at the receiver and are acknowledged. The sender cannot advance the window past 5 until 5 is acknowledged. And so the window is what's called stalling. The window can stall, where although most of the data in the window has been delivered, it can't move past the first unacknowledged piece of data. So it can't advance the window past that. The receiver also maintains 3 variables. It has a receive window size, the last acceptable segment. So this is the last segment that it will receive and won't drop on the floor. If it receives a segment past this value, it'll assume something is wrong or it's not going to buffer it and it'll just discard it. Then there's the last segment it's actually received. And so the receiver is then maintaining this invariant, that the last acceptable segment minus the last segment received must be less than or equal to the receive window size. And so if you have a receive window size equal to 5 and a last segment received equal to 3, then it's not going to accept anything past 4, 5, 6, 7, 8. Right? So if it receives suddenly segment 10, it won't accept it and it'll drop it. Now, if the received packet is less than this acceptable segment, then we'll send an acknowledgement.
And so if it receives any of these packets, it will send an acknowledgement. Now, in the basic case, the way most sliding window protocols work, these acknowledgements are what are called cumulative acknowledgements, such that you send an acknowledgement for not the data you received, but rather what is the end of the contiguous data that you received. That is cumulative. If I acknowledge 3, that means that I have received 3 in everything before it, not just 3. And so it represents a cumulative state of reception across the entire communication. So in this example, if a receiver has received 1, 2, 3, and 5, and then suddenly receives 5, it doesn't acknowledge 5, it acknowledges 3. Now there are some protocols that can do things like actually do selective acknowledgements, but the basic case is that you use cumulative acknowledgements, which is cumulatively what is the contiguous chunk of data that you've received. So one little detail here, TCP doesn't acknowledge the data it's received, but rather n+1. So TCP acknowledgements are in terms of bytes. And so if TCP is received up to byte n, its acknowledgement packets will say n+1. So it's the first byte of data that's expected. So if you're ever looking at a TCP trace or trying to see how the TCP protocol works, just keep this in mind. The acknowledgement value in a TCP header isn't the last byte received, the cumulative acknowledgement, rather than the next byte, the first missing byte. So one of the things we talked about in the stop and wait protocol was that a counter of size, a 1-bit counter, was sufficient, assuming the packets weren't delayed more than a round trip time. So what about in sliding window protocol? Suddenly we have a receive window, we have a send window. How big a sequence number space do we need? So a receive window is always greater than 1, send window is always greater than 1, greater than or equal to 1, and the receive window is is less than or equal to the send window. This is because if the receive window is ever greater than the send window, it's a waste. The sender would never have those packets in flight, and so there's this extra buffer space which will never be used. However, there are cases where the receive window can be smaller than the send window and the protocol still works. So here's one interesting basic case of that called go back n. Well, let's say we have a receive window of size 1 and a sending window that's larger than 1. Well, in this case, we're going to need sending window size plus 1 sequence numbers. So what does this protocol look like? Well, the sender, let's say it has a send window size is equal to 3. So the sender sends 0, 1, and 2. And let's say those are all acknowledged. And so the receiver acknowledges 0 and acknowledges 1 and acknowledges 2. Well, when it acknowledges 0, the sender is going to send 3. Slide the window forward. When it acknowledges 1, it's going to send 4. And when it acknowledges 2, it's going to send 5. So now let's say that 3 is dropped. Now the receiver is going to still receive 4 and 5, and so it can act 2. It's going to send act 2, act 2. The sender is going to time out and resend 3. So this is called a go back n protocol. Because the receive window was size 1, the receiver could not buffer 4 or 5. And so when a single packet is lost, in this case 3, the sender has to go back in. It has to retransmit the entire send window worth of packets. It has to retransmit 3, it'll have to retransmit 4, and it'll have to retransmit 5. In contrast, if the receive window size had been 3, then the receiver could have buffered 4 and 5. The sender would only have had to retransmit 3. Then you get an ACK 5, and it could go on and send 6, 7, 9, 8. And so here, in the case of a go back n protocol, you need the send window size plus 1 sequence numbers. Because you imagine if you have only the send window size, there's 0, 1, 2, and then remember what happened in stop and wait when there's a packet delayed where, hey, let's say that the ACK for 0 is delayed, there's a timeout, you retransmit 0. Now you can't distinguish whether or not the delayed acknowledgement was for the retransmission or for the old data. Generally speaking, if the two windows are the same size, you need twice basically their sum, and so that's the generalization, that you need RWS plus SWS sequence numbers. You need a sequence number space at least as big as the sum of the window sizes. So that's the basic sliding window algorithm and the algorithms that the sender and the receiver use and how the sender manages the window. What does this look like in TCP? So TCP is a sliding window protocol and uses that for flow control. And so here's the TCP header. And so the way TCP works is the receiver specifies a flow control window using the window field, this in terms of bytes. And so it basically says, this is the buffer size that I have on the receiver, and so the set of packets that I will accept. And the basic rule is that here are the data sequence number and the acknowledgement sequence number. And so a TCP receiver will only handle data equal to the acknowledged sequence number plus the window. And so the sender isn't allowed to send data past ACK plus window. That's to make sure it doesn't send data which the receiver is not going to buffer. And so this is a way for the receiver to essentially set what the send window size is. So let's walk through an example. So here, again, I'm going to talk in terms of packets rather than in bytes, like in TCP. And here's the sequence number space for the packets from 0 up to 29. So let's say that we have a receive window size equal to 2, and a send window size equal to 3. So communication begins, and the sender is going to send 0, 1, and 2. Let's say all three of those packets arrive, and so the receiver receives 0, it's going to acknowledge 0, it's then going to receive 1, acknowledge 1, receive 2, and acknowledge 2. When the sender hears ACK 0, it'll advance the window, the send window, and it'll send 3. When it hears the acknowledgement for 1, it'll advance the window and send 4. When it hears the acknowledgement for 2, it'll advance the window and send 5. Now let's say that packet 3 arrives successfully and is acknowledged, but packet 4 is lost in the network. So now we have this case where ACK 3 has been sent, packet 4 is lost, then packet 5 arrives at the receiver. Now the receiver is going to send another acknowledgement 3, again because of cumulative acknowledgements. And so now the sender heard ACK 3, then another ACK 3. Waits, times out, and resends 4. So it'll resend 4. And let's say 4 arrives. Now this receiver can acknowledge 4, so it can ACK 4, but because its receive window was of size 2, it actually had 5 buffered, and so it can also acknowledge 5. And so it'll send ACK 5. So a sliding window flow control algorithm allows an unacknowledged, so a whole window of unacknowledged packets to be in flight. And so what this allows is if you can set that window size appropriately, it allows a sender to be able to actually fully utilize the capacity that the receiver has, unlike a stop and wait protocol where you can have at most one packet in flight. When acknowledgements arrive for new data, the sender advances the window. Generally, sliding window protocols use cumulative acknowledgements. And the exact sequence number space you use depends on the window sizes. So it turns out TCP uses a large sequence number space just for ease of use and to really be robust against heavily delayed packets. But if you're implementing your own protocol, you may be able to get away with something a little bit smaller.